So what we are going to do in this video is see TLS Handshake in action using Wireshark. So Wireshark is a network analyzer. It's an open source network analyzer that you can download for free from the internet. What Wireshark lets you do is hook into a network interface and start listening to the packets that are flowing through that interface. So let me start by explaining the setup that we have here for the video. We have the standard client server setup. The client being the browser in this case. I'm going to use Chrome for this demo. And the server is written in Java using Jetty. So this server is serving HTTPS traffic, and the HTTPS certificates right now that I'm using are self-signed. So the client, which is the browser, can access this server on the URL HTTPS because we are we are doing a TLS connection. The protocol that's used here would be HTTPS. Localhost 8443. So I'm serving the traffic on the loopback interface on port 8443, and it's going to be on protocol HTTPS. So whenever a browser opens up this URL, it would be served with a page from the Jetty server. So what we are going to do as a part of this video is open up Chrome and then basically visit this URL, HTTPS localhost 8443 on Chrome. What this would do eventually is basically the browser would initialize a TLS handshake because for setting up a HTTPS connection, TLS handshake becomes necessary. Um, And what we are going to do is we basically hook up Wireshark on this local interface, the loopback interface. We start listening to all the packets that are flowing in the loopback interface using Wireshark and capture the packets that are flowing between the client and the server. So here, when the client initiates the TLS handshake, it sends a bunch of packets to and from the client and the server. So we are going to capture those packets and view it using Wireshark and see what each packet is sending. Either the client, what client is sending to the server, or what server is sending back to the client. So if I open up my terminal, I'm already in the directory which has my Java code, and it's written in Gradle. So if I have to run, I do Gradle run, and this should start my server. So while this is coming up, let's go ahead and also open Chrome. That's required for the demo. So in Chrome, we're not going to directly open Chrome. There is one tweak, one setting or one environment variable that we need to set so that it's going to help us later in the video. But I'll tell you why we are setting that environment variable later. But for now, let's just set the environment variable and just be with it. So the environment variable that I'm setting here is SSL keylog file, and it's pointing to a file in my user directory called sslog.txt. So this is an empty file right now, or this file might not even exist. But what happens is when I open Chrome with this environment variable set, it's going to create a file called sslog.txt, and it's going to write some contents to it. We'll see what that content is in a while, but for now, let's just set this up. So once that environment variable is set up, as you can see, I'm already in the Chrome install directory, so I can go ahead and do chrome.exe, and that would launch the Chrome browser for me. So I now have Chrome open, and I also have my Jetty server running. I can verify that by visiting the URL that I just mentioned. So as you can see, I'm being presented with a 404 page because I'm not serving anything on the Jetty server, so it's just a blank 404 page. But even for serving this page, the client had to set up a TLS connection. So there was a TLS handshake happening in the background, but we couldn't see it. So for web developers might be very familiar with this, where they would go to the inspect tab network, and whenever they reload a page, they see all the HTTPS requests or the HTTP requests that are going through the browser. But underneath this, there is also TLS connections that being set up that is not captured in the browser, or there is no way in the browser that you can see these packets. So that is where Wireshark comes in. So let me open up Wireshark as well. So In Wireshark, what we're going to do is, since I'm serving my traffic or my application, since it's running on local host, I can just start listening on the loopback traffic interface. Um, that would give me, I mean, that would basically clear out all the noise that's going on my Wi-Fi network or any other network that I'm connected to. So this will basically narrow down the traffic that I'm capturing. So I'm just going to start listening on the loopback interface. So once I start listening on the loopback interface, as soon as I start, you can see a bunch of packets um, going through this interface. So we're not going to go into these packets for now. What we're going to do is we filter out these packets so that we only see packets that are going to the server. So the server is currently running on port 8443. So if I have to filter all the packets that are going to and from that port, I would do tcp.port is equals to 8443. And once I hit enter, it should clear out all the packets and start filtering. So now what we have is essentially done is basically we are only listening to packets that are going to the server and that are coming out of that server. So whenever a client in this diagram contacts the server, that packet is captured because it's going to 8443. And whenever a packet is coming out of the server to the client, even that packet is captured is because that 8443 is the source port in that case. So if we go back to the browser and if we check what's happening in Wireshark, you can see that there is no content yet because once we started capturing, we haven't visited the port 8443 from the browser. So now what we are going to do is go ahead to the browser and just do a reload, and this would basically populate the packets in Wireshark. So once we have this, um, what we are going to do is pick one connection. That there are, I guess, two TLS handshakes happening here. I'll go with the second one. I'll follow TCP stream. Okay, let's hope this has all the data that we need. Yeah. So the first three packets that you see on the top in this TCP stream are basically the TCP handshake. That's essential for establishing a TCP connection. So that's basically the SYN from client. So whenever a client wants to set up a TCP connection with a server, it basically has to start with a TCP handshake. So the client is the one which initiates the TCP connection. The first message is from the client, which is from port 61549. That's the Chrome browser. That's the port allocated on the Chrome browser. And the destination port is 8443. So it sends a SYN packet to the server, and then the server responds with a SYN along with an acknowledgement, and then the client would reply with acknowledgement packet. And these three packets ends the TCP handshake, and then TCP connection is established between the client and the server. And from the fourth packet, if you see you see that it's the protocol here is TLS version 1.3. And in the info section here in the table, you can see that it's called a client hello packet. So if we look at the TLS handshake, the first message that's sent from the client to the server is the client hello message. And the client hello message, if we open up the TLS, the transport layer security segment of the packet, you can see there is a TLS record and handshake protocol message, which is client hello. So I open it up further. And if we see the client hello message, if I open it up, there are a bunch of there is a lot of information that's being sent from the client to the server. So the points of interest here for us are the cipher suits. So basically the client is advertising that these are the cipher suits that I support, and it's up to the server to pick one of these cipher suits based on how secure they are. So what the client is doing here is basically is advertising these cipher suits, and the server is later going to pick one of these cipher suits. If you go back and see what else is being sent, Uh, the other point of interest for us here is the key share. It's being sent as an extension. So what key share essentially is basically in the previous versions of TLS, either TLS 1.0 or TLS 1.2, what's going to happen was initially server, the client was going to advertise the supported um, cipher suits, and then the server had to pick one of those cipher suits, and then the Diffie-Hellman parameter used to be sent to the server from the client. So, but in case of TLS 1.3, that round trip, that one round trip is eliminated. And the first message, the client hello message, now contains the Diffie-Hellman parameter. So you might ask, how would the client know what Diffie-Hellman function that the server is going to pick? The client doesn't know at all. What it does is it just guesses that this is the group, or this is the Diffie-Hellman function that the server is going to use. And it basically sends a corresponding Diffie-Hellman parameter for that function that the client thinks the server would choose. So here, if you see, once we expand the key share extension, there are a couple of functions that the client thinks that the server would pick. Uh, this is one, and if I expand this, this contains a key exchange. This is the Diffie-Hellman parameter that's being sent for this uh, Diffie-Hellman function. And the second one is x25519. This is another Diffie-Hellman function, elliptic curve Diffie-Hellman function, and the corresponding Diffie-Hellman parameter is also sent with that. And if we scroll down a bit, we also see that the client is going to send the supported signature algorithms. And yes, so that's about it. Those are the important components that this client is going to send to the server. And once all this information is sent, there is an acknowledgement packet back from the server saying that I have received the previous packet. So this is standard TCP where each packet should be acknowledged. So that is the acknowledgement message that we get in return. And then once the client has sent the client hello message, the server responds with the server hello message. And if we expand what's going on in this message, you see that the cipher suit is selected now. So the server responds back with a single cipher suit that it has selected from the list that is advertised by the client. So now the communication, the encrypted communication is going to be set up on this particular cipher suit. And then if we look at the key share extension, what's happening here is out of those two key share extensions, or the two functions, the Diffie-Hellman functions that were advertised by the client, the server has picked one, which is x25519, and it has sent its own Diffie-Hellman parameter. So what happens in a Diffie-Hellman setup is each side of the exchange basically sends their own Diffie-Hellman parameter, and this parameter is later going to be used to basically deduce the shared key between them. And the shared key which is deduced is basically used to do the encryption using a symmetric key algorithm. So that is the reason they exchange a key. So the round trip that was basically happening in the previous versions of TLS is now eliminated. It's only one round trip where both the client and the server would have um, basically have the required Diffie-Hellman parameters, and now they can actually set up a encrypted connection. So now that both uh, share a deduced key, what server does is sends another message called chain cypherspec. What this message basically tells the client is basically whatever packets that are going to come out of the server from now on are going to be encrypted. And the next message, as you can see, this is going from the server to the client because the source port is 8443 and the destination port is 61549. This basically tells that this is from the server to the client, and you can see that it contains encrypted application data. So as we have just seen, chain cypherspec basically tells the client that from now on, me as a server is going to send you encrypted packets. So as you can see, this is encrypted application data, and this is just some garbled text for us. This doesn't make any sense to us at the moment. The client then sends back a chain cypherspec message, letting the server know that now on client is also going to respond back through the encrypted channel, and it has some encrypted application data again. And then for some reason, it sends uh, finish message and closes the connection. I'm not sure if I'm following the right TCP stream, so let's go back and change the stream. Let's try picking the first TCP stream. Okay, even this looks similar. This is 92 again. Let's go back, pick another one. TCP client hello. Then another client hello. There is another client. Let's try to follow this. Okay, looks like this is the entire connection. This is the connection through which the HTTP data is served. With the previous two connections, I'm not sure why those are being established. When I do it with curl, those connections are not established, but Chrome for some reason basically establishes um, those connections and then does a finish, closes the connection. But here you see all the this is probably the entire connection where the HTTP data is also being served. This is the same again. You have the standard client hello, the server hello, chain cypherspec, then the server sends the encrypted application data. The client does chain cypherspec and starts sending application data, which is encrypted. So for anyone that's listening to our connection, there is no way for them to decrypt this application data, the encrypted application data. So for anyone snooping on our network, for an attacker who is basically listening to our network, they would see this garbled text, and for them, there is no way to basically decrypt and make sense of this data. But for us, fortunately, there is a way, and we already have made preparations for that. When we basically in the terminal, if you remember, when we are opening Chrome, we have set this environment variable. So Chrome uses OpenSSL in the backend for setting up TLS communication. So what this environment variable tells OpenSSL, OpenSSL recognizes this environment variable. And what it does is basically starts storing all the encryption keys that are deduced at the end of the Diffie-Hellman key exchange into this particular file. So what we can do is basically point Wireshark to this particular file so that it has access to the decryption keys. So we'll do the same. So if you go to Edit Preferences and under Protocols, we search for TLS. There is this section which says pre-master secret log file name. So we can paste the file name here. And once I hit OK, you can see that there is a refresh that's happening back in Wireshark, and it starts decrypting the packets. So after change cypherspec, you see that the message here, which is column number 608, the row number 608 is encrypted application data. But once I hit enter, you see that that packet is going to get decrypted because we have the encryption keys that are used here in this SSL log.txt file. So once I hit OK, you can see that after change cypherspec, the message now is decrypted. So if we look at the decrypted message, what it essentially has is the server is going to send its certificate to the client. It's going to send a certificate verify message. Certificate contains the standard certificate with the signature and public key of that server. And the certificate verify is basically sent to prove the ownership of the private key that's corresponding to the certificate. So what certificate verify contains is basically server hashes the contents of all the messages that are passed between the client and the server up until this message. And then basically for the hash generator, it basically signs it using the private key. And that signature is basically part of the client verify message. And what the client can do here is basically do the reverse, where it basically starts hashing all the messages uh, that are exchanged up until this point, and then it basically creates the hash out of it. Once the hash is generated, it uses the public key of the certificate, and basically decrypt the signature. And the decrypted signature should be the same as the hash that's generated by the client. Once that's verified, it knows that the server is the actual owner of the private key that's associated with the certificate. And then the server finishes with the server finish message. The server finish message contains the hash of all the packets that are exchanged between the client and the server up until this point. So the finish message, the hash is only sent to basically make sure that there is no tampering that happened during the handshake. And then we know that the client is going to do the change cypherspec, and it has sent some encrypted application data, but now it's decrypted, and we see that the data that's sent is the finished message. The finished message here is again verified data, which is going to be again a hash of all the messages that are exchanged between the client and the server up until this point. And even this is done for the same reason, to make sure that there is no tampering that happened in between. And once since both server and the client has sent the finished messages, this marks the end of the TLS handshake. And then basically the application data starts flowing through. Here, since the protocol is HTTPS, the data that's going to flow here is the HTTP data in an encrypted form. So the HTTP that you see here is the plain text HTTP GET request that the client is sending, and the server responding here with a 404 page. If I expand it, you see the server responding with a bunch of HTTP headers and also the body. So the only reason why we're able to see this HTTP data in plain text right now is because we have the decryption keys that are essential for decrypting this data. We only have those keys because we have set an environment variable that basically allowed Chrome to store it in a file. So right now you see this HTTP data, but in a standard TLS connection, once it's set up for the outside world, what it would look like is if I go to preferences again, go to protocol, and go to TLS again, and remove this file reference, then you see that the same packet just says application data, and it's just some encrypted data that's being passed between the client and the server, and no one can make any sense of it unless you have access to the keys that are used for encrypting this data. Since this is a symmetric algorithm that's used for encryption, you can use the same keys for decryption as well. So that is why the encryption keys are basically used to decrypt the same data. I'll go back and revert this and point Wireshark to that file so that the data is decrypted. And once the server has responded with the HTTP data, the connection is then closed. And this packet basically closes the connection. This marks the end of the connection. So that is all for this video. So if we go back to the summary of what we have seen um, how the packets are flowing between the client and the server, how our TCP connection is established, the first three packets, the TCP handshake. Then we have seen the TLS handshake, how it's happening. And after a point, you have seen that the data is encrypted, but we have also decrypted those packets by having access to the encryption keys, and it is done using setting this environment variable and opening up Chrome. This environment variable currently works with OpenSSL backends. So Chrome, since it uses OpenSSL, this works, but for Firefox, this might not work. And for curl, this works on Linux. The environment variable works on Linux if you're using curl as your client instead of the browser, because curl on Linux uses OpenSSL as a backend for HTTPS or TLS communication, whereas curl on Chrome, curl on Windows uses some different backend for TLS communication. So I hope this video was helpful. I hope you had a better idea of um, you now have a better idea of how TLS communication is set up between the client and the server. Um, I guess that is it for the video, and I'm going to publish this video along with an article on basically breaking down the different versions of the TLS protocol, the handshake specifically. So I'm going to also link down the required resources to understand most of these packets that are flown between the client and the server. Yeah, so that is it for this video. Thanks for watching.